Hi everyone, my name is Emma, and in this video, our group is going to be presenting our project, the Integrated Photonic Circuit Testing Platform. The picture in front of you shows the final design of the project, rendered in SolidWorks. We will walk you through our design step by step, and then show you how we finally evaluated it using various tests. First, let's introduce the team. We split up the work for the project based on the type of engineering it required. Peter and Hirak worked on the mechanical aspects of the project. Peter created the main platform that moves the chip around, whereas Hirak created the arm that holds the lasers. Hirak also worked on the software side of things and helped integrate our project with the existing SciEpic code. I worked on the electrical and software sides of the project. I built the circuit and programmed our own control code. Additionally, we all had input on each other's parts and were consistently up to date with each team member's work. Here is an outline of our presentation. We will start off with some background on our project, which leads into our proposal. Then we will go into the design of the project and also the testing done to evaluate the design. Finally, we will go into the logistics of the project and finish everything off with a final note.
Integrated photonic circuits use light instead of electricity to carry information. They can carry information faster and use less energy than traditional ICs because light encounters little to no resistance on its path as opposed to electricity. However, these circuits face some drawbacks that make large-scale implementation impossible. The biggest challenge this technology faces is a lack of data. Data about the quality of circuits produced using a given manufacturing process is hard to come by due to the infancy of this field and the capital investment required to make the testing platform.
This brings us to our proposal. Our product will be a cost-effective two-dimensional positioning platform that could work with photonic circuit chips in the micrometer range. Note that our product was developed to be used by UBC SciEpic, a photonics laboratory, to test these chips. However, it could also be used in other applications, such as observing a variety of different samples under a microscope, or very precise laser engraving. We can now look at our design specifications. Our device needs to be cost-effective so that it can be an alternative to current more expensive models. The platform of the device needs to be able to travel in a 10 by 10 millimeter space so that it can easily move around the entire surface of a chip. The resolution needs to be at least micron so that it can move very precisely. Next, we want the device to be able to withstand a lot of uses so that it does not need to be replaced very often. We also need the device to be linearly accurate, so we don't want any parasitic motion moving the platform off course. Finally, we want our system to be safe to use, to have all the wires neatly tucked away and the rest of the system neatly integrated.
We have separated the platform into two parts to decouple movement from certain aspects of calibration. The platform is entirely responsible for movement and for calibrating the test chip so that it lies flat with respect to the laser head or the light probe. The arm is responsible for rotating the probe to align with couplers on the chip and to adjust the distance between the test chip and the probe.
Hello everyone, my name is Peter, and right now we're going to talk about the main platform of our project. On the right you'll see a diagram representation of the driver mechanism that we developed, and on the left you'll see a video showing the final implementation of that mechanism. Our stage needs to move in 1 micron increments over the range of 10 millimeters. In this design, we used a stepper motor to create precise rotation without feedback controls. To convert the rotation of the stepper motor into linear motion, we used a lead screw and a lead nut. The shaft of the lead screw is coupled to the shaft of the motor using a rigid coupling, and the nut is fixed to the lever system input. The lead screw has a pitch of 0.3 millimeters, which means one step of the motor moves the nut by 3/2000ths of a millimeter, which is 1.5 microns. Also note that in the diagram, we see two linear shafts. The shafts are there to guide the motion of the lead nut and to assure that it moves in a straight line. Next, focus your attention to the left side of the diagram, the lever system. This is a simple system that reduces the motion of the lead nut in order to achieve the final desired step size. This diagram shows two lever configuration for a 100-fold reduction. However, we simply used a one lever system with only 3-fold reduction. This brings our final step size from 1.5 microns at the nut to 0.5 microns at the end of the lever system. Now please focus your attention to the video. In the video, we see the motor, the red rigid shaft coupling, the lead screw, the lead nut, and the linear shafts and bushings. The lever system is in green and the blue parts are fixed relative to everything else. You can see that in order to conserve space, the lever system is actually folded on top of the lead screw system, whereas in the diagram they were separate. This was possible because of 3D printing. The next slide shows two rendered images. The one on the right is an early CAD model which showcases the fundamental arrangement for the two driving mechanisms. Note that the moving mechanisms are now encased in a linear flexure. This flexure assures the motion is straight. Please note the footprint of the device. Our printer was barely large enough to print this. However, printing both moving mechanisms at the same time assures that the platform moves correctly and with little parasitic motion. Finally, in the left image, you can see the final CAD model. Extra mounting holes were added, a photonic chip holder was attached, and the entire assembly is made more symmetric and robust.
The arm is mounted on the same table as the stage with M5 by 1.25 threaded rods and square extrusions. The enclosure for the mechanism is attached to the extrusions with extrusion supports, which are holes that are drilled into the sides of the enclosure. The arm performs its function through the use of 3 shaft collars. To actuate the probe, you need to release the shaft from the middle and top collars and move it to the desired height above the chip by turning the outside screw. Then you need to engage the top collar and rotate the shaft by turning the side screw. Note that the shaft rotates while the Z-axis shaft collar is still engaged because the collar and the Z-axis lip are not rigidly connected. That is, they allow rotation about one another. Then the middle shaft collar is engaged to lock the shaft in place and ensure that the probe does not move out of its calibrated position.
Next, we will look at the electrical system and how it integrates everything. In this simplified control diagram, we can see that our software outputs to the circuit, which allows us to control the two stepper motors independently. This allows us to move the platform in both the X and Y directions. Here's a slightly more complicated control diagram. It shows the different components of the electrical system. We used an Arduino for a microcontroller because it is a reliable and cost-effective option. Then we used two A4988 stepper motor drivers that allowed us to microstep the motors. This is important as it makes the spinning of the motor a lot smoother. Our system needs to be very precise, therefore we want to try and eliminate as much vibration as possible. Finally, we use two stepper motors, one for each axis. Here we could see 3 different pictures of the circuit. In the upper left is the design of the circuit, showing how everything should be connected. The one on the right is the physical prototype, which works relatively well. However, the connections aren't ideal because they're not permanently connected. The one on the bottom is the PCB schematic. It should improve the connections of the circuit as everything would be soldered on. Unfortunately, due to COVID-19, we could not integrate this into our project. The software for a system can be split into 2 parts. The first part is a motor control code specifically made for our system. The small snippet you see on the screen includes important things such as how many microsteps are we using and how fast is the motor spinning. We control the motors using the Arduino serial monitor by typing in the amount of steps we want it to spin.
SciEpic already has software for its original testing platform. Their code can process the vector files that they use to determine where the couplers are. perform calibration and control the peripheral devices, such as the temperature control unit and N77 detector. So we decided to modify their code to send displacement instructions to our Arduino and let the Arduino control the motors to actuate the platform. That is, the SciEpic code figures out how far the stage needs to move, and then the Arduino moves the stage.
For our project, we did multiple different tests. However, please note that we could not do all the tests we wanted due to COVID-19. The first tests we did were in Ample at UBC. With the help of people from SciEpic, we were able to use high-quality microscopes to track the movement of our platform. The following videos show these tests. The next tests we did were to test the accuracy of the device using the Arduino code with the serial monitor. This part was a little difficult because we had to do it at home, which means we couldn't firmly connect the platform to the table, and so there were some unwanted vibrations. We also had to reprint a slightly new platform design consisting of only one axis. As you can see in the picture, we have two dials attached. The reason we have two dials is to test for the linearity of the movements. We tested for the number of microns per full step of the motor. The tests we did were to move the platform the same number of steps multiple times, each time recording the resulting dial measurements. This allowed us to take the average and find the most accurate final answer. The reason we had to take large steps was because the dials are very sensitive and are a lot more consistent with higher step counts such as 500 rather than smaller step counts such as 5. With the testing we did in the lab, you could see that there was some parasitic motion. The platform did not move perfectly in a straight line. This could be accounted for in the software. For the tests done at home, our results are that each full step moves the platform around 0.355 microns per step. This was calculated by taking a lot of measurements at different step counts. Notice how as the step count rises, the number becomes higher. However, even at 2,000 steps, the number is off from our calculated and expected value of 0.5 microns per step. There could be multiple things causing this, such as the dials not being very accurate, or that there are faults with the mechanical components or the motors. We could potentially fix this by adding in some microsteps to bring it down or up to an easier number to work with, such as 0.5 microns per step. The following cost breakdown chart shows everything we paid for in order to make the final product. This is not equal to the total value of the product, because in that case we wouldn't include the costs of prototyping or the costs of the dials. In terms of socioeconomic change, this product can help the scientific community test more photonic circuits. The current platform setups are very expensive and difficult to acquire, and our product is an alternative cost-effective option. This could improve the research currently being done on these circuits and bring more advancements to the field. Additionally, note that PICs can bring advancements to many different fields, such as quantum computing, which is at the front line of innovative technologies. In terms of keeping things environmentally friendly, the majority of our product can be reused or recycled. The 3D printed parts can be melted and the mechanical pieces can be stripped from the device and reused. The electronic components can also be either reused or recycled. Finally, we will end this presentation with a final note. Due to COVID-19, we couldn't do some of the things we planned on doing. As mentioned before, we couldn't order PCBs for our device. This contributes to our product not being as polished as it could have been. We also had to scale down to a single-axis platform in order to simplify testing at home. The testing was harder to do and not as high quality as we would have liked. We had to manually read the dials after inputting step values into the serial monitor, instead of having it automatically print values from feedback. All in all, we finished our product and it works mostly as intended. With our device, we are capable of moving a sample less than 1 micron per step. Our design requirement was to have a resolution of 1 micron per step. This means our resolution is better than what we needed. However, we still need to work on the precision and accuracy of the device. Thank you for listening to our presentation. We hope you've enjoyed learning about our product.